All right, problem 21. P implies Q is equivalent to not P or Q. Another way to write this is P implies Q is equivalent to, that's what this symbol here means. This is equivalent to not P or Q. And this is another shorthand way to write or. You can write and by doing the upside down triangle. Now, it's a good idea to just memorize this identity and also to memorize this one. But if you only memorize this other one here, you can also derive it. So we have P implies Q is equivalent to not Q implies not P. And we actually talked about this one earlier and did a truth table for it and everything. So if you only memorize this one, you can probably derive this. And the way you would do it is kind of assume here that this is correct. So what we're doing is we are taking the first term and we're going to not it. We're negating it. So we're going to try that again here with this. So we're going to take this first term, not Q, and we're going to not that. We're going to negate it. We're going to go not, and then we have not Q. That's what that first term is. Then we're going to take this symbol here. We're just going to do an or. And then we're going to take the second term, which is Q, right? This is that second term here. We're just copying it over. But if we were to do that from this term right here, we would just copy over the not P. And then what you can see here is that we have not Q, which is the same thing as Q, or not P. And, you know, not P or Q is the same thing as Q or not P. The order doesn't really matter because it's an or statement. Either one is true or the other one is true. So if you know one of these, you can derive, proof that the other one is true. The other way to go about it, which takes longer but is a little bit easier to not fuck up. But the first thing you want to do is fill out the columns for P and the column for Q. And we have every single possible combination here. Either P is going to be false and Q is going to be false. P is going to be false and Q is going to be true. P is going to be true and Q is going to be false, or they're both going to be true. That is every possible combination that we can have. And you can write T or F if you want to. I like to use 0 and 1, where 1 just means true, 0 means false. But also recall that, P implies Q is a logical statement where we say if P is true, then in fact Q is true. And you can think of real-world examples like the one we were talking about earlier. If my dog is wagging his tail, then that means my dog is happy. So if P is true, then Q must be true. That is the whole implication that we are kind of asserting to be a fact. And now all we need to do is look at this. We look at P and say, okay, this is a 0 and Q is a 0. But here's the thing. If P is false, we can't really make any observation about whether or not this whole statement is true. If I say if my dog is wagging his tail, then he's happy, but that doesn't necessarily mean that if my dog is not wagging his tail, that he's not happy. So we can't prove that it's true. Therefore, this is going to be vacuously true because our original premise is false. P here, in this case, is going to be false. And if that's false, then it doesn't really matter what Q is. And then likewise, we're going to do the same thing again. P is false here, so we don't really care what Q is. We're just going to write that this is vacuously true. Now here what we're going to say is that P is true, but Q is false. And that is saying basically that my dog is wagging his tail, but he's not happy, which makes this entire implication false. I can't claim that my dog is always happy when he's wagging his tail if in this particular scenario he's wagging his tail but is not happy. And then finally we have the implication where P is true and Q is true, meaning that my dog is wagging his tail and he is happy. Therefore, this is true. It confirms the statement, if my dog is wagging his tail, then he's happy. So what we have here is the truth table for P implies Q, where it's 1, 1, 0, 1. Now, in order to figure out if we have an equivalency, all we need to do is look at not P, and when we're doing not P, all we're going to do is reverse what we have written for P. So we're going to have 1 instead of a 0 here, then we're going to have another 1 instead of a 0, and then here we're going to have a 0 instead of a 1, and we're going to have a 0 instead of a 1. And now what we want to do is look at not P or Q. If either one of these is true, if either one of these is a 1, then that means that this entire expression is going to be true. So we look at not P and we look at Q. We know that not P is true in this case, so this is going to be a 1. And again, we look at not P. This is true. We don't even really care what Q is. It is true too, but we're just going to put a 1. And then we look at not P or Q. Well, not P is a 0 and Q is a 0, so this is the case where they're both false. Neither of them is true, so this is going to be a 0. And then finally we have not P, 0, or Q, and Q is a 1, therefore we can write 1. And you can see that we have the exact same truth table for P implies Q as we do for not P or Q. So therefore these things are equivalent.